I would like to welcome you all to this KBA event. This is a very fantastic opportunity for us to all listen to Professor Sagawa and his fantastic innovation of the neodymium iron boron permanent magnet. My name is Ole Eriksson and I am going to be the chairperson for this event. This is an event that comes to play and comes to you because of the professional aid here at KBA locally, and also thanks to Professor Johan Åkerman in the audience, who was instrumental in making this happen. So we are very happy to have the speaker here today. We're very happy to see all of you here. I should also say that some of you are expected to have lunch at the KBA Villa, and unfortunately we don't have room for everyone, so if you are going to have lunch at the Villa, you should have had an email. If you have not had an email, there is a Pressbyrån kiosk a little bit further down the road, unfortunately. They have good hot dogs, but that's basically it. Sorry for this, but that's how it is. I should also say before we start that there's a very nice brochure outside from Tokyo University. You're welcome to grab it, bring it with you, read and be informed. With this strengthen the Swedish-Japanese connection and research collaboration. And with this, I welcome Professor Sagawa to the stage, please.
Okay, thank you very much. I'm very, very honored to be here. Okay, I talk about this neodymium boron magnets, invention, industrialization, and basic research. Yes, this is a human history, ancient, medieval, early, modern, ... Okay, magnets have had great impacts on human society. For instance, navigation compass played a pivotal role in the era of geopolitical discovery. However, it was until the 20th century that powerful permanent magnets with magnetic field and magnetic forces suitable for industrial applications appeared. Since then, permanent magnets have been developed in a complementary manners with electromagnetic products such as motors, generators, and radars. And this continues to the present day. As a result, the record values of the maximum magnetic energy products of permanent magnets have been increasingly exponentially. Okay, what is BH maximum? BH maximum is BH is the product of B and H. A rectangular area under the BH line, as you see, which means the work done by the magnet. And BH maximum is the maximum of the product of B and H. And BH maximum is therefore maximum work that can be done by the magnet. So this is a good figure of merit for comparing magnets. So this is the evolution of the world's strongest permanent magnet. And the BH maximum increased exponentially, as you see. And now, neodymium and boron is the strongest. How did I invent the neodymium and boron synthesis magnet? I explain the story by linking together the contents of the papers I was involved in. Okay, this is my first paper on the rare earth cobalt permanent magnets. I was in Fujitsu laboratories, and the title is Rare Earth Cobalt Permanent Magnets with Improved Mechanical Properties. Paper was published in 1979. And while researching how to improve the mechanical strengths of samarium cobalt magnets, I kept thinking, why aren't there any rare earth iron magnets? Iron is much more abundant than cobalt on Earth. Iron has a large magnetic moment than cobalt. I became confident rare earth iron magnets will be in strong need in 10 years. Not at that time, but in 10 years, it becomes necessary. But how can I realize rare earth iron magnets? Okay, this shows the global situation surrounding permanent magnets. At this time, in 1970s, samarium cobalt magnets developed. And I was here. I started research on rare earth iron magnets in this period. Okay, in this period, researchers were racing for BH maximum of samarium cobalt magnets. In this period, an academic conferences, magnet researchers were busy competing for BH maximum with samarium cobalt magnets. No one seemed to care about the potential of rare earth iron magnets. No one was talking about rare earth iron compound. There was little data on rare earth iron compounds. How can I realize rare earth iron magnets? I thought and thought every day, but had no idea. But one day I had a clue in this symposium held in 1978, January 31st. The title was From Fundamentals to Applications of Rare Earth Magnets. In this symposium, the first speaker, Professor Masaaki Hamano, had this talk entitled Phase Diagram of Rare Earth Cobalt Systems and Magnetic Properties of Rare Earth Cobalt 5 and Rare Earth 2 Cobalt 17, almost about the rare earth cobalt systems or magnet. But he took 3 minutes or so explaining why don't rare earth iron magnets exist. He explained, showing this crystal structure. Iron distances are too long, too short for a stable ferromagnetic compound. And his explanation was based on the paper of Dominic Gibault. I expect him very much. I know him. Okay, at that time, I got an idea. Carbon or boron may expand the iron-iron distance. So the story goes like this. The idea of rare iron boron and rare iron carbon permanent magnet, I proposed this as a new research topic. But company was not interested in this topic. Then how about this? I proposed the development of applications of spin reorientation of neodymium cobalt 5. This was accepted as an official research topic. And this is a paper on the spin reorientation of the neodymium cobalt compound. The title is Temperature Sensitive Neodymium Cobalt Compound Produced by Powder Metallurgy. I was working here at Fujitsu laboratory. And in this paper, I presented SR, spin reorientation temperature shift due to M, additive element in neodymium cobalt M5, where M is iron, aluminum, manganese, tin, zirconium, silicon, and showed the temperature range can be varied widely above and below room temperature. And I proposed various applications of SR materials, such as thermal sensors, thermal bulbs, magnetocaloric material for magnetic refrigerator. Please note that I was getting close to neodymium and boron sintered magnet, because this SR material is also produced by sintering. So 1988, I was promoted to a manager. I had little time for research. I needed to change the company to continue my pursuit. And next year, big idea of neodymium boron sintered magnet I had. I proposed it, but the company was not interested. So I proposed it to Sumitomo Special Metals. Sumitomo Special Metals, SSM, welcomed my idea very warmly. SSM promised at this time to provide as many staffs and as much research funds as necessary. The president promised me. So I entered Sumitomo, and almost 2 years later, I published this paper, 1984. This is the first paper on the neodymium boron sintered magnet. The title is New Material for Permanent Magnets on the Base of Neodymium and Iron. And I was at the Sumitomo Special Metals. The paper was published in 1984. And oral presentation of the paper was made at MMM conference, Magnetism and Magnetic Materials Conference, on November 10, 1983. The venue was a room at the Hilton Hotel in Pittsburgh, and it was filled with an audience of over 500 people. The person next to me is the chairperson, Professor Carl Sturner, who discovered samarium cobalt magnets. In this paper, I presented that we found a new ternary tetragonal compound for permanent magnets. And tetragonal crystal structure with lattice parameters, we determined A, 0.880 nanometers, C, 1.221 nanometers. And we also determined the single phase region as the neodymium 12 iron 82 boron 6 atomic percent. And this was the first study, first truly ternary permanent magnet compound of 3 different groups of elements, namely rare earths, iron group, and transition metals, and light elements. And these figures shows compositional dependence of magnetic properties. On the left, neodymium content dependence. On the right, boron content dependence. And we determined 15% neodymium and 8% boron. This composition, neodymium 15, boron 8, iron 77, this composition, we determined this composition as the core of the new product called NeoMax. And this shows the dependence of coercivity on annealing temperature. Coercivity shows at 870 K at peak value. And this shows SEM image of the neodymium iron boron sintered magnet. This consists of the main phase and the neodymium rich grain boundary phase. It proved that the microstructure is ideal for the nucleation type permanent magnets. This shows changes in magnetization and demagnetization curves of this neodymium 15, boron 8, iron 77 NeoMax magnets due to magnetizing field. And fully magnetized BH maximum shows 290 kilojoule per cubic centimeter. This is world's strongest magnet. This is a new record of the energy product. And this is evolution of the world's strongest magnets after invention of the sintered neodymium boron. And BH maximum, when it appeared, BH maximum was 290 kilojoule per cubic meter. And after that, the record, world record, was improved many times to reach to the almost the upper limit of the neodymium boron magnet. This is a theoretical, almost theoretical limit. And this shows my laboratory and the team at SSM. SSM provided staffs and research funds as the president mentioned, promised me. And this was my plan. My development team proceed with A, B, and C in parallel. A, material development. B, development of production technology. And these are the most important as researchers in company. But we will conduct the basic research in parallel. Basic research. Number one, precise measurements of magnetic properties of rare earth 2 iron 14 boron compounds. Single crystal preparation. We prepared single crystal preparation and high field magnetic measurement. Number two, phase diagram of neodymium iron boron system. Number three, study of coercive force, relationship among coercive force, magnetic properties of compounds and microstructure. And this is my second paper with SSM, presented while I was very busy developing and implementing the production process. Okay, this is the second paper from Sumitomo. And in this paper, we presented the basic data of the rare earth 2 iron 14 boron compounds with almost all rare earth elements. These data are based upon anisotropic sintered magnets. And we, in the early stage of development, we noticed neodymium iron boron magnets have poor temperature stability. So it's necessary to increase coercive force. From this data, we had an idea of adding heavy layers. As you see, this table shows so necessary magnetic data for almost all layers to iron 14 boron, including almost all rare earths. So we have the data from about the anisotropy field HA. The higher the HA, it's easy to increase coercivity. So by changing from neodymium to iron 14 boron to the terbium to iron 14 boron or dysprosium iron to 14 boron, the anisotropy field increase. So we predict that coercivity can be increased. So we made magnets. This addition of dysprosium increased coercivity. We solved the problem of poor temperature stability. And industrialization became possible. And when cobalt was mixed with neodymium 2 iron 14 boron, the Curie temperature increases, as you see, the Curie temperature increases very rapidly as the cobalt content increases. And however, coercivity, as you see, the coercivity decreased by the cobalt addition. HCJ decreased by increasing the cobalt content in the sintered magnet. So we cannot increase the coercivity, cobalt so too much. So cobalt addition is limited to 5%. This value. Okay. This is a third paper. In the third paper, we presented the result of strong magnetic field measurements of single crystal rare earth 2 iron 14 boron compound. From this time, Satoshi Hirosawa joined the research team and strengthened our lineup, plus full cooperation from IMR, Tohoku University. Okay, so this is a magnetization curves or data of 3 typical compounds. Combination of single crystal samples and IMR Tohoku University's strong magnetic field device, perfect magnetization curves data were obtained. Neodymium 2 iron 14 boron, this is a typical compound with C-axis anisotropy. And this is a typical compound with basal plane anisotropy, samarium 2 iron 14 boron. And yttrium 2 iron 14 boron. This is a typical compound with rare earth non-magnetic. So we had a very basic data completely. We had the perfect data. Okay, so this is a phase diagram paper. In permanent magnet, the study of the phase diagram is extremely important. Immediately after the development of the neodymium iron boron sintered magnet, I assigned Yutaka Matsura in charge of studying the phase diagram. And we had a rapid response. Yes, this is a phase diagram. The phase diagram was established very quickly. And it turns out this is a iron neodymium boron ternary phase diagram, and this is ideal in this sense. First, among T1, this is a neomax composition, and T1, T2, and neodymium. Among these three compounds, only the T1 is not magnetic, and the T2 and neodymium non-magnetic. This is important to get good coercivity. And second factor is ternary eutectic point E2. T1 is here, and T2. This is a eutectic point. I'm sorry, E2. E2 exists at the bottom of a deep valley, very deep valley. This is important. Why? Because by this condition, this is the best to form the ideal cellular structure. This is important to get coercivity to form cellular structure. And what is necessary is the thickness of boundary phase is thin and non-magnetic. And this is realized by the fact that the E2 is very deep. Therefore, by this phase diagram, we have very good magnetic properties. And also, it's easy to see. From this cross-section of the phase diagram, it is clear that the bottom, the eutectic point E2 is very, very deep at the bottom of the deep valley. And okay, this, as I mentioned, this enables cellular structure with the neodymium-rich phase 2 to 3 nanometers, very thin. This is important to get a high coercivity. And what is important is the neodymium-rich phase. The boundary phase is almost non-magnetic. This is also important. So we have very good magnetic properties with neodymium boron system. So my research team established the framework of the mass production process: melting, crushing, jet milling, pressing in magnetic field, and sintering and annealing. Okay, in the world production of sintered neodymium boron magnet, mass production begins 3 years after invention. It's very fast. 1985, invention was made in 1982, and 85 we started the production, the quantity of which is 100 tons, and the next year 200 tons, and 1988 more than 400 tons a year. So I have to say this, another inventor of the neodymium boron magnet. I invented, as I mentioned, neodymium iron boron sintered magnet, and Dr. John Claude invented the neodymium iron boron magnet produced by melt spinning method. Melt spinning method. Melt spinning method. And and by this method, the different by we これはこっちか。
一番上です。一番上。
え？
一番上のボタン。
一番上か。はいはい。これそうそう。Yes, yes. We use to form alloys ordinary casting, but his method is using belt spin, and by this method they can produce different type of permanent magnet, resin bonded magnet, hot pressed isotropic magnet, and hot deformed anisotropic magnet. And typical representative inventor of this type of magnet is John Claude. And about this type, myself. And okay, this is a melt spinning method. Dr. Claude's idea and approach. Dr. Claude discovered that melt span neodymium boron alloys exhibited excellent permanent magnet properties. This shows a rapid solidification. Okay, rapid solidification with melt spinning method. And by this method, the industrialized product developed from melt span neodymium boron alloys, not sintered magnet, but bonded magnet, resin bonded magnet, or hot deformed magnet. By this method, the ring method, plate-like method, plate-like magnets are produced. Okay, and this shows the magnetic properties of various neodymium boron magnets. Okay, the BH maximum and the coercivity diagram. As you see, the neodymium iron boron sintered magnet that we developed is in this area, and the neodymium boron hot deformed magnet, plate-like shape magnet is in this area, and ring magnet type hot deformed magnet is in this area, and this is neodymium boron bonded magnet area. Okay, the neodymium boron bonded anisotropic magnet were produced by other group later. Okay, neodymium iron boron magnets used in hard disk drive, spindle motor, neodymium. In this here, the neodymium iron bonded magnet is produced, and the voice coil motors, neodymium iron boron sintered magnets is used. And thanks to neodymium boron magnets, hard disk drives have become very compact and can be installed in personal computers. And it is no exaggeration to say neodymium magnets opened the information society. Neodymium magnets used in air conditioners, it helped make life more comfortable for people all over the world. Neodymium magnets used in world EVs in order to prevent global warming. We must continue to move forward with the shift to EVs. Neodymium boron magnets in action, wind turbine and motor for industrial robots. Neodymium boron magnets are widely used in robots to increase factory productivity and in wind turbines to contribute to prevent global warming. The invention of neodymium boron opened up a new era of truly ternary permanent magnets composed of three different groups of elements. It is rare earth, iron, and light elements. The early stage basic research, as explained above, served as a bridge to further understanding and improvement of neodymium iron boron. As the world's strongest permanent magnet, sintered neodymium boron magnets played a key role in innovations in information technology and the transition to green energy, and the demand for them will continue to grow. Thank you for your attention.